Good evening. Tonight is our last lecture, and we'll be discussing three topic areas. The first is physical storage, the second is system architectures, and the third is data analytics. A secondary storage covers technologies used to store data with access times far longer than those used with primary storage, which is a random access memory. Secondary storage systems generally have capabilities far greater than main memory, and you're looking at, for example, 2 terabyte hard disks today compared with 8 gigabyte RAM for your typical computers today. A secondary storage uses magnetic and optical storage technologies, and solid-state flash technologies are rapidly replacing magnetic-based devices. Historically, IBM shipped the first disk drive in 1956 as part of its 305 Ramex system. It had a platter that was 24 inches in diameter, and its capacity was 5 megabytes. In 1983, the PC disk drive was introduced by Seagate, and it also stored 5 megabytes, but it was only $1,500 and small enough to fit inside a PC. And again, today we have hard drives on your typical PCs being sold with capacities of 500 gigabytes up to a terabyte, and their cost is usually $50 or less. The disk drive uses a technology that we've understood since the 1940s. It's actually a direct descendant of the phonograph that was invented by Thomas Edison in 1877. The DVD Blu-ray devices store data by changing the optical properties of the surface of a track, while magnetic disk stores data by magnetizing the surface of a track. A disk drive uses a flat rotating platter that's covered with a very thin layer of a material that can be locally magnetized. And you're going to magnetize it in one of two directions, north-south or south-north. This platter rotates under a head that magnetizes the surface of that platter to create a track of ones and zeros. When data is retrieved, a read head is normally co-located with a write head, detects the magnetization of the surface, and uses that data to the magnetization to reconstruct the recorded data. In practice, the construction and operation of these real disk drives is extremely complex because the size of the magnetized region is very small and the disk is rotating at very high speeds. So here we see a graph of the density on the disk drives in terms of megabytes per inch from the 1950s up to 2010. And you can see it's been rapidly increasing at a logarithmic rate during that entire period. So we classify physical storage media with regard to the speed and the cost. And we also can classify it in terms of volatile storage or non-volatile. Memory is volatile. When you turn off the power, you lose the data. Memory is also extremely fast, but it's also extremely expensive. Disk drives are non-volatile storage. The data is persistent, and you retain the data even when the power is switched off. It's cheap compared with main memory, but it's slow relative to memory as well. So cache is the fastest form of memory storage. And then we have main memory. And again, both of these are volatile. They lose their contents if the power fails. A magnetic disk is persistent storage. And it works by again, magnetizing sections of a platter that has a magnetic surface. So it began in the early days of computer technology, and the magnetic disk drive relies on electromechanical machinery that have moving parts. That makes it somewhat vulnerable to mechanical failure and gives it a shorter mean time between failure than something like main memory. Magnetic recording techniques have been used for a long time, and there was an idea that magnetic technology would be replaced, and that's been a persistent rumor for the entire time that we've had magnetic devices with personal computers. But magnetic storage technology kind of stubbornly refuses to go away in spite of its inherent limitations. And of course, the same is true for tape storage as well. We keep finding uses for these various systems. The magnetic properties of certain materials are probably the most obvious means of storing data, because magnetism is an excellent binary recording medium. The magnetic particles can be charged in terms of the north-south or south-north, and that makes it perfect for detecting a 0 or a 1. The read head, and we see a picture of a read head here, is the structure of the read-write device, and it's the structure for reading data on a magnetic recording media. Very early recording heads consisted of ferromagnets with a few turns of wire around them. Again, constructing read-write heads is difficult because of the complex interacting requirements of the recording system. The air gap has to be really narrow. If it's large, the area of magnetism is also large, and that reduces the number of bits that we can store on a device. So instead of having 1 terabyte on a disk, we'd have 5 megabytes as we loosen all the elements we see in the various components of the hard disk systems, including that air gap in the read-write head. It's also necessary to build the heads with a ferromagnetic material that can support a strong field. A strong field is required to magnetize the particles on the recording medium. The head material must also have a low remnant magnetization, and that's a residual field that's left on the platter after the write current has been turned off. If the remnant magnetization is too high, then the magnetized bits that you just recorded can be disturbed. And so you might get errors on your disk. There's physical limits to the magnetic recording mechanisms, just as there's limits to the number of bits that can be stored in a square inch. And there's been various theories about how we won't be able to extend the capability of magnetic disks. But as the anticipated theoretical limit of each theory is reached, the physicists and engineers working on this technology always find ways of extending beyond that theoretical maximum. So we also have another storage technology, optical digital storage. And that's another alternative. It was really waiting to happen, and it was inevitable that we would get optical storage. It's just a matter of waiting to see which technology would predominate and which technologies would get to the marketplace first. So we have three optical recording mechanisms used by digital computers: the CD, the DVD, and Blu-ray. The difference between these is largely one of scale. As time has progressed, it's become possible to scale down the size of the features of the disk that stores, the optical disk that stores the data. Philips developed the laser disc in the early 1970s, and it became a marketable product in the 1980s, and very popular. It shared a lot of the attributes of today's compact discs, but it was an analog technology. The system was read-only, and only a few films ever made it to this technology. During the 1970s, Philips and Sony joined forces to develop optical storage, not least because Philips had considerable experience in optical technology, and Sony had expertise in encoding and error correction mechanisms. So when Philips and Sony worked together, one important achievement was the standardization of recording and playback mechanisms. So two fundamental parameters are the size of the CD itself and the sampling frequency. The disk's diameter is 12 centimeters, and the sampling frequency is 44 kilohertz. And this is a standard. So the first practical low-cost optical storage mechanism was the CD, introduced in 1981 as a means of storing high-quality sound. The structure of a CD is similar to a magnetic disc because information is stored along a track on a platter. A CD's track is continuous and arranged as a continuous spiral. The spiral has about 20,000 turns, which corresponds to a length of about 3 miles. The effective density is 16,000 turns per inch. And of course, the theoretical limit is much higher than that. Digital information on a CD is imprinted on the surface with pits of varying lengths. The pits are coated with a metallic mirror and a protective layer. And then the region of the surface that is not indented is called a land. data is read from the disk's surface by illuminating it with a tiny spot of light and then detecting how much light is reflected back from the surface. A change in reflected light intensity occurs every time the laser spot moves from the pit, which has that metallic surface, and the land. A magnetic tape is yet another mechanism for storing data. And magnetic tape provides a means of archiving large quantities of data. And we live today in a world where the production of data is estimated to increase by 60% compounded annually. So archival storage is vital, and hence magnetic tape is still a thriving market. In the 1960s and 70s, the preferred medium was magnetic tape because it was relatively cheap and could store large volumes of data. Data is stored on tape as parallel tracks. Magnetic tape recording technology is virtually identical to disk technology, except there's a single track that is 1 bit wide along a long flexible magnetic tape. Most magnetic tapes are 2,400 feet, for example. A tape drive required a very large and powerful motor because it was the actual tape itself was heavy compared to the platters of a disk. And you could typically get tapes that were 10.5-inch reels up into the 1980s, and data was stored at about 128 characters per inch. So all the tape systems have a long latency because the tape has to be moved past the read-write head, and a desired data may take several seconds, or even minutes to move as you unwind the tape from one reel to another, and it goes by the read-write head. So today, tape is used purely for an archival medium. You need direct access disk technology or flash memory to store that type of information if you're going to be using it real time. Tapes in the past were used to store data that were used in batch operations. Today, it's archival. It's an archival system. So the tape drives have grown smaller, and the tape cartridges have also grown smaller over the years. By 2010, you had a 1/4-inch cartridge that was becoming obsolete, and they started getting into even more exotic ways of storing information that decreased the size even more. It's a popular myth that the tape and tape cartridge recording technologies are obsolete. As I mentioned, the death of tape is much exaggerated. A Fuji film just this past summer in July of 2020, last month in fact, announced a 400 terabyte tape. So we see continually declining PC sales since 2012, and that's actually resulted in declining disk drive sales. But this has not impacted tapes, which are used for archival of huge data sets. You never really had a large market of home users for tapes. They didn't need it to archive their data. With the growth of large data sets that we need for AI and the massive amounts of data coming in from the Internet of Things, we need archival storage that can be cheap and easy to use and store. And tape fills those needs. And the archival market continues to grow. It's a $1.1 billion market in 2019. So we also have, well, here's a hierarchy of magnetic tapes. At the bottom, used for archival. Optical disc also is another means for archiving data. In fact, optical discs were actually used for archival of data on PCs. Because you had the built-in disc to the CD reader and DVD readers on the PCs, and they were made read-write so that you could write data out to optical disc. Magnetic disc was used for your standard transaction operations, and then you had flash memory for storing things, perhaps like an operating system that you knew you're going to be reading in all the time, and it could be read in quickly. Main memory, very fast, and then cache memory is super fast. We also have the rise of solid state disk drives, and the days of the magnetic drive may be limited by the introduction of solid state drives, and they mimic the hard drive electrically. Solid state drives use semiconductor flash technology to store data. The SSD, solid state drive, has considerable advantages over the electromechanical disks. The most important are it has lower power consumption, lower weight, a higher performance, and probably most important, it has a greater tolerance to shocks. So you don't get these head crashes when you bump things. So primary storage is going to be our fastest memory, media, but it's volatile, and it's going to be cache and main memory. Secondary storage is next in the hierarchy. It's non-volatile. That means it'll persist the information even when the power's turned off, unlike memory or cache. And it's moderately fast. And then tertiary storage, it has a very slow access time, and it's used primarily for archival purposes. And there's where we have our magnetic tape and optical storage. So let's look at how data is actually stored on a disk and how the recording and playback process works. So the read-write head steps in towards the center or out towards the periphery of the platters. As the disk rotates, the head describes a circle on the platter that's called a track. A track is too large a unit of data to be practical, so the track is divided into sectors. And a sector is the smallest unit of data that can be read from or written to a disk. So some of the things to consider to reduce the physical size of a disk drive and increase its disk capacities, disk manufacturers co-locate several platters, as we see here, on the same spindle. And the read-write heads that read each surface are connected to the same actuator. So all the heads line up in the same overall sector. And as we see here, you have about 50 to 100,000 tracks per platter. And then you have maybe 500 to 1,000 tracks, sectors per track on the inner tracks, and 1,000 to 2,000 sectors on the outer tracks of the platter, which have, of course, a larger circumference. A sector size is going to be typically 512 bytes. And then the disk arm is going to swing to the appropriate track. And then as the platter spins, it'll pick up the sectors on that track that are of interest. So should the head fail to follow the surface, and it hits the surface, and it'll be hitting it at about 50 miles an hour, it could damage the magnetic coating and actually destroy some of the data on the disk. And this, again, is known as a head crash, and it often occurs with magnetic magnetic disk drives when there is a shock to the PC. So here we have a disk subsystem, and we've got multiple disks that are attached to a controller, and the controller attaches to the system bus. The system bus moves at the clock speed for the CPU and the main memory. They're going to be much faster than the actual disks that store data and are needed. That data is needed in the operations for the computer. So there's an intermediary between disks and the system bus known as the disk controller. So the disk controller takes the signals from the system bus, and it will then read the appropriate sectors on the right disk drive, and then store it in the disk controller memory, and then when the system bus asks for it, it'll provide it. And it does this through a system of interrupt requests. And so when an IRQ comes in for the disk to read, it reads, and then when it has the information, it sends an IRQ, and then the CPU will access the disk controller through the bus to get the data that it needs. We also have disks that are not directly connected to the computer system. And so one of those approaches is storage attached networks, and that's a large number of disks connected by a high-speed network to a number of servers. And then we have network attached storage, and that's a file system interface where using a networked file system protocol that is used to store the information. And here we see some of the transfer times, seek times. Seek time is how long it takes to find a particular track and a sector on that track. Rotational latency is once you're on the right track, how long does it take to get to a particular sector? And then the data transfer speed is how fast you can read the data on the disk and send it back to main memory. And then mean time between failures. With the magnetic disks, it's up to 5 years typically when you start having your failures, your first failure. And then you're going to have to do a disk repair. And most operating systems have the ability to do disk repair. So if you didn't lose something critical, then it just will repair. And by repair, it means it bypasses the parts of the platter that might be broken or damaged. So another approach to improve the redundancy and the robustness of disks, and also improve their performance, is RAID. And this was developed in 1987 at UC Berkeley by Patterson, Gibson, and Katz. And they developed a paper they called A Case for Redundant Array of Inexpensive Disks, like you see here. And the RAID concept became extremely popular. So there's several different ways you can organize clusters of disk drives together, and they became RAID levels. So disk drives are inherently a serial storage mechanism. In a RAID system, multiple drives are operated in parallel, and the bits of a single file are divided between the individual drives. They're not all stored on one drive. So RAID arrays, again, can be used to improve the performance of disk systems and also improve their reliability. By replicating data across several disks, the failure of a single disk can be made invisible to the system. So there's two important concepts with RAID. The first is that data is recorded on the disks in sectors, and the second is each sector has a frame check sequence that can detect one or more errors in the sector. So error checksums are typically used, and you probably remember from your beginning computer science course things like even parity and odd parity. So you add an extra bit onto the end of a byte, and if it's an even parity and the byte ends up with an odd number of ones, then you make it a 1 to give it an even parity. Otherwise, you make it a 0. So you'll be able to detect any errors that might happen. So that's an error detecting code. You also can add even more bytes bits to the byte to get an error correcting code, not just error detecting, but you can actually correct errors. And so they become quite sophisticated in the use of these check sequences to detect errors and perhaps even take corrective action from them. So RAID level 0 is the only level that doesn't use redundancy to provide additional reliability. At level 0, RAID with N drives will divide the data into N stripes that are applied in parallel to the N drives. And we see in the diagram where we've got non-redundant striping. The size of each disk should be the same. Otherwise, the effective use of RAID arrays defaults to the size of the smallest disk drive in the array. And so you get wasted space on the others. The advantage of RAID 0 is its high throughput. For N drive, the capacity is N times that of a single drive, and the speed is higher because the read operations can take place in parallel. The capacity of a RAID 0 array with N drives is simply N times the capacity of one drive. That is, we don't lose any capacity because of error checking or redundancy. Now, one of the disadvantages, the loss of one disk brings down the entire system. So a RAID 0 array only makes sense if the data is frequently backed up and provision is made for failure between backups. Figure B in the slide illustrates a level 1 RAID mirroring array. And that replicates copies of stripes on multiple drives. So data security is increased because you can remove one of the drives without losing data. So we've got 4 drives and we mirror the data, we copy it to 2 different sets of drives. So if we lose one drive, we still have the ability to use its complement in the set of mirrored disks. So the write time is longer for this, and it's the longer of the 2 parallel writes. Most accesses, however, are reads, and so it doesn't really have a big penalty there. So the other thing to consider about level 1 RAID is it's expensive because it duplicates data. But that really has become less of a concern because, again, you can get very capable disks for under $50 and very large capacity, high speed disks for about $100. The efficiency of the RAID 1 is 50%, simply because the data is duplicated. Duplication does give you excellent fault tolerance. If a drive fails, the system can continue working. So the other RAID levels 2 and 3, employ multiple synchronized disk drives, and that is the spindles on the different drives are synchronized so that sector I passes under the read-write head of each of the disks at the same time. And you store parity checking bits on some of the drives. And that way you can, if you lose a drive, you can, if you lose a drive, you can use the parity bits for that drive and recover the data. So level 2 and 3 arrays do provide true parallel access in the sense that typically a byte is written to each of the disks in parallel. The difference between levels 2 and 3 is that level 2 uses a Hamming code to provide error detection and correction, whereas level 3 provides only a simple parity bit error detecting code. The parity check data in level 3 is stored on one disk, whereas the Hamming code of a level 2 is going to be spread over more than one drive. And as we see in this one, it's spread over 3 drives. RAID levels 4 and 5 are similar to levels 2 and 3, but in these cases, the individual disks are not synchronized and they operate independently of each other. The stripes are much larger than we have in levels 2 and 3. In level 4, we have block interleaved parity, whereas in level 5, the parity stripes are interleaved and stored on the disks in an array. You can update the parity information in RAID 5 systems more efficiently than you can in RAID 4. So here, again, a discussion of how RAID 4 works, and then a discussion on how RAID 5 works. And you can see that the parity bit information is actually stored on all the disks that you're actually storing the information as well. So RAID 5 is a popular configuration today. It provides a striping as well as parity for error recovery. The parity block is distributed among the drives of an array, and that gives it a more balanced access load across the drives. A minimum of 3 drives is required for a level 5 array system. And then level 6, similar to level 5, but stores redundant information to guard against multiple disk failures rather than just one disk failure. Some of the factors affecting your choice of RAID level, the cost, the performance you need, where do you need the performance? Do you need it in improving the read speed, or do you want to have improved reliability and tolerance of failure? And then how easy is it to rebuild a RAID system in the event of a failed disk? RAID 0 is used only when data safety isn't important, typically on home PCs. 2 and 4 have been replaced by 3 and 5. So they aren't used as much anymore. Level 3 is not used since bit striping forces single block reads to access all disks, and that wastes your disk arm movement. And then level 5, which uses block striping, kind of avoids that wasted disk arm movement. And level 6 is rarely used because you have level 1, which is mirroring. Obviously, level 1 costs more in terms of disk costs, but level 1 and level 5 usually have enough security for the applications that we are using in business today. So you can also have software RAID, where the RAID's done entirely in software and you don't need any particular hardware. You can also have hardware RAID. But with hardware RAID, a power failure can result in corrupted data on the disk. You also have the ability to do hot swapping, and that's where you replace a disk while the system is running without powering down. And that, of course, is very convenient for maintaining extremely high availability. Okay, let's talk about the database system architecture and how it's changed over the years. One approach to analyzing industry direction is to see how the computer architecture is optimized for the major constraints that exist at any given time. We can look at 3 phases in computer architecture based on the scarcities of the computer platform that had to be dealt with, and the optimization that was done by the computer platform to address those scarcities. So during the 50s and the 60s, CPU cycles, memory, and hard disk space were all scarce. So the core abstraction of that era was programming languages like COBOL and Fortran that efficiently use a single computer, and it was for batch oriented systems. But when we got disk drives, we started getting multi-user systems, and that proved to be something of a strain on the old centralized mainframes. So here's a centralized computer system. You have your CPU and memory. You have disk controllers that would control the disks. And then you have graphics adapters that provide a support for monitors. And then you'd have also controllers that would go out for printers and remote keyboards, and a serially attached RS-232 serially attached monitors. With the introduction of microprocessors in the 1970s, memory and CPU cycles were no longer the limiting factors they were in the 50s and the 60s. So in the 70s, we changed the core abstraction to reflect the memory and cycle abundance on the client side. And so you began to get more sophisticated GUI, graphical user interfaces. And likewise, you started to see the rise of client-server databases. That technology came into its own. And a new scarcity, bandwidth, became a prime limiting factor in that era. So with a client-server system, you have the server, which handles something, for example, like database operations. And then your business logic and your graphical user interface was on a program on the client. And then your client would access the server for whatever the server provided. Let's say in this case, it was a database server, it'd get data, and that would be sent back to the client, which the business logic in the program would use and present results to the users. And you had a network that was connecting all these clients to the server, and data was going across the network to all the clients. So bandwidth became a limiting factor in that model. Now, you also have the back end, which is going to be used for services like mail or database or some other system level service. The front end, which is going to be on the clients, is going to be things like forms and report writers and graphical user interface facilities. Again, this is another view of what we just looked at in terms of client server. So client server systems really challenged the centralized mainframes by putting out networks of workstations or personal computers connected to back-end server machines. It provided a better functionality for the cost, had better user interfaces, and easier maintenance. After we had the client server systems, then we started to see the rise of transaction servers. Microsoft Transaction Server was one of the first. Corba kind of preceded that. It was developed by IBM. Microsoft extended that with MTS, and then J2EE took MTS, Microsoft Transaction Server, and applied it to the Java world. And with the rise of transaction servers, we no longer had to write programs where we concerned ourselves with multi-threading or managing database connection pools, database connections are extremely expensive for a database. And so in the past, you'd have to watch out for having too many database connections, or you could bring down the server. So with a transaction server, the programmer no longer had to concern themselves with these. You write your program as if you're writing it for a single user, and you deploy it on a transaction server, and the transaction server is going to handle those issues for you. So we also have data servers, and they have the ability to ship data to clients where it's processed, and then the shipped results come back. A data server has a disadvantage in that it's sending a lot of data that's not necessary over to the client. The client picks out the information that is necessary and then works with that, and then sends the entire result set back to the data server. So the modern databases like the SQL Server and Oracle and so on, they only send the result sets you need to the client where it's worked on in the with the business logic. Parallel database systems are coming into their own. We talked about the need for these in the rise of NoSQL databases, and you also have parallel systems coming out for big data. Hadoop is an example, but it was a batch-oriented because it was relatively slow. Spark is a kind of new replacement for Hadoop. It's about 100 times faster than Hadoop, and it again is working with parallelism. And here's a distributed system. The idea that data is spread over multiple machines or nodes. So you've got replicas of your data at various sites, and the network interconnects them, and data is shared by the users on multiple machines. And then, of course, you have the issue of updates in distributed systems, and we touched on those briefly with our lecture on NoSQL databases. Homogeneous databases are where all the hardware and software is the same. Heterogeneous distributed databases is where you can use different hardware and software, and that way you can inexpensively add to and quickly add to your network. Some of the networks that we're dealing with will be local area networks, and that's where the computers are distributed over a small geographical area, such as in one single building. Wide area networks need a more powerful routing protocol, and so, but they're networks that deal over large geographical areas. And so you have a variety of different routing protocols in a wide area network for getting the data efficiently from one location to another. And here we see the typical setup of a local area network, your server, and then you have a variety of workstations and computers, and a printer even on the network. A groupware like Lotus Notes can work on WANs with the ability to replicate the data and then update the various replicas. If the system becomes partitioned, we can replicate the data and maintain eventual consistency if it does become partitioned with groupware type applications like Lotus Notes they mention here. Okay, let's take 10 minutes and then we'll come back and talk about data analytics.